I don't think I need to explain to this audience why graphs are a useful thing. So I'm just going to jump right to a demo. So is there anyone here that does not know what a Bacon number is? As in Kevin Bacon. Okay, how about a Bacon-Erdos number? Okay, so basically, you just add, so Kevin Bacon is a somewhat mediocre actor, but he started in a lot of movies, and the conjecture is that every other actor either starred in some movie with him or starred in someone else, with someone else that also starred in a movie with Kevin Bacon, and that the distance between every other actor and Kevin Bacon is, I think, 6 at most. And so Erdos is a famous mathematician that published a lot of papers, and the conjecture is that every other person who published papers is somehow connected to him in a very short path. And so a Bacon-Erdos number is the sum of the two numbers. So does anyone here have a Bacon-Erdos number by any chance?
Omega plus 3.
Really? What is it?
At least, I don't know. No, under 9, whatever. I mean, I was next try in a movie, and so I have a finite Bacon number, and I.
Great. You win. So this is sort of like that.
What's the PLT number?
Yeah. So this is sort of like that, except in the context of PLT, which is the name of the Racket dev team. So I wrote a program. It goes to this website, scrapes. This website has a bunch of papers written by people at Northeastern and other places. It scrapes all this data and throws it into a graph. And then we can, that's big. And then we can do some computation on this data. So here I'm running a web server, thanks Jay. And to compute a PLT Bacon number, you give it 3 authors. So the first author is the person whose number you want to compute. Let's choose, how about me? And then we have to choose a Bacon author. Oops. How about, let's see, who's here? How about John? And for Erdos, how about Matthew? So we can compute. And so my Clements number, I published the paper with John. So my Clements number is 1. I have not published the paper with Matthew yet, but John has published the paper with Matthew, and so my flat number is 2, so my Clements flat number is 3. Should we do one more? How about Ryan? Who else is here? Burke? And how about Vincent? And so, let's see. Ryan's Fesher number is 2, and Ryan wrote a paper with Vincent, so his Fesher St. Amour number is 3. If you want to represent networks like this or any other relation, a graph library is very handy. And so let me show you the one that I wrote. Okay. So my graph library, I borrowed a lot of ideas from the C++ Boost graph library. The authors of the Boost library, Lee, Seek, and Lumsdain, in their OOPSLA 99 paper, they did a survey of a lot of existing graph packages. And what they found was that basically none of them applied the principles of generic programming and were far more rigid than necessary. In other words, they weren't very flexible, they weren't very extensible, they hard-coded a lot of things, and the code wasn't very reusable. And so they took what they found, formulated a bunch of principles that they wanted a graph library to have, and that is what eventually became the C++ Boost graph library. And so I thought they had a lot of good ideas, so I borrowed a few of them. In particular, I want to talk about 3 genericity goals that I wanted to have for my library. And the first one is that I wanted to be able to define new graph representations that work with existing algorithm implementations. So in the same paper, the authors of the Boost library said that they found there were as many graph representations as there are applications of graphs. So there's a whole bunch. And so if you restrict yourself to just a few representations, your library won't really be that useful. So I wanted to be able to define new representations, and Racket made it very easy to do that, specifically define generics. Thanks, Vincent and Asumu. Am I missing anyone else? And I believe this is sort of like protocols in Clojure, but essentially you just define an interface, and then I implemented algorithms following this interface, and then you can define new graph representations where you implement methods of the interface, and you get a nice extensible system. So far I just implemented a handful of pretty standard algorithms, but if anyone out there likes implementing graph algorithms, please contribute. So the second goal that I wanted to have was when you read a graph algorithm, you often come across something like this, so this is for the description for depth first search, and it says, to do depth first search, you first color all the vertices where each vertex is initially white, and then when you discover it, you color it gray, and then when you're done with your search, then you turn it black. And so at a higher level, this is a property that you want to attach to your graph. And so in my graph library, you can do pretty much exactly that. So there's a define vertex property form that takes a graph, that's G here, a name, and here it's color, and here I'm initializing everything to white, all the vertices to white. And so here is the beginning of a depth first search algorithm, so when in the library, if you define a property, then it also defines getters and setters here. So the getter here is named color, and the setter is named color set. And so it's very easy to define a depth first search function that pretty much matches the description on the previous slide. So the third goal was that what the Boost authors found is that there are a lot of common patterns in graph algorithms that were not being exploited. Pretty much all the algorithms were separately implemented and not doing any code reuse. So I wanted to avoid that. So here's 3 sample graph algorithms. You don't actually have to read the details, but what I want to show is that they pretty much all have the same shape. This is breadth first search, Dijkstra's shortest path, and Prim's algorithm for computing a minimum spanning tree. So they all pretty much have the same shape. They just differ in a few details. And so if you just abstract at a few key points, then you can implement them all in the same way. And so that's what my library does. So there's a generalized breadth first search that takes in, it has hooks. The Boost library calls them events. Basically, they're just higher order functions. The function also takes a queue that satisfies a generic interface. And then it just calls these hooks while doing the search so that you can customize it. So here is, you don't have to read the code, but I just wanted to show that I can implement Dijkstra search using this generalized breadth first search. It's okay, it fits on one slide here, but it's still a little bit noisy. There's some lambdas here that are kind of ugly that you can maybe get rid of. So I just wanted to show a few tricks that I did in Racket to make it look nicer. So, okay, so here is breadth first search generalized. The library also has a separate do BFS form that sort of cleans things up. And so here I've added keywords to represent the hooks, and I've gotten rid of the lambdas. Instead, following each keyword is a list of identifiers that you name that represents the current vertex in the traversal and its parent. And then you can use these names in the subsequent expression. And Racket makes it incredibly easy to do this. So here I use syntax parse, Racket's secret weapon. I guess Racket has a lot of secret weapons that we heard of today. But thanks Ryan Culpepper for syntax parse. It's really, really awesome. It has a very expressive pattern language that you can just pretty much define anything. So here I'm using the optional pattern, which says that you don't have to specify each hook if you don't want to. Oh, I'm missing some default values, but right, the optional just says that you don't have to include a parameter for each one, and then the or says they can occur in any order, so I can flip them out of order if I want, and then to implement the binding forms, it just expands into the lambda that you saw in a previous slide. Question?
Yeah, for those who might not be familiar with syntax parse, what are the ellipses?
Sorry, yeah, this is kind of confusing. So this ellipses is actual syntax. It just means that I want one of these, and then there are several of those in a row. And then this I use to hide some code. So yeah, sorry. It's really confusing. I agree. Yeah, you're right. Sorry. Yeah, that was my fault. Okay, and then just one more thing. So then I realized that I was always binding the exact same names, so I didn't actually need the list of identifiers. Instead, I created special identifiers that are that you can use in scope in the body of each hook. And this is sort of like, reminds me of Clojure's lambda abbreviation, where there's the %1 and the %2, the special identifiers that are available. So Racket lets you define your own. Here, my graph library defines from and to as special identifiers. There's a couple other ones. If you're interested, you can read the documentation. But again, Racket made it very easy to implement this using syntax parameterize. It lets you define lexical macros that behave differently depending on the context. And so this will just do the right thing here. Here I'm in the body of the event. It's remapping the special identifier to the actual variable that represents the vertex. But then outside of this scope, I can define it to be an error if you try to use it in the wrong place. And so, again, Racket made it very easy. So that's all I have. If you want to try it out, it's the same thing you've been seeing all day: Raco, package, install, graph. And I would love to hear any feedback. Thank you.
Do you have a list of algorithms that are particularly interesting to you to have included that are not yet implemented?
Not really. I was talking to someone today that was mentioning A star, but basically anything that's fairly widely used would be great.
Ask for list of names right here now.
Put it on the GitHub.
Okay.
Can you or do you plan to support Erwig's functional graph interface where you can build graphs inductively by adding and removing edges?
Yeah, so it would be nice. I realized I had some setbangs in there, which may be a faux pas. But you can actually do it functionally, because the hooks that I showed you actually carry accumulators that get strung through. It added extra code on the slide, so I had a setbang. But you could actually do it functionally. But I guess my goal was not to implement new algorithms, and the algorithms that I want to implement just happen to be imperative. But I agree, it would be nice. I don't know if I'm going to get to it anytime soon.
Cool.
So one of the goals that the Boost Graph Library people had is for it to run really fast. So can you say anything about performance?
So it's a really good question. I have not done thorough benchmarking. I guess I would say that you get Racket speed. And so, the algorithms are pretty standard. The complexity is known. I ran one test that was, I think I found it from a Stanford algorithms course that was several million nodes, and it did like strongly connected components, and I think it was about maybe 5 times slower than C, but it's reasonable.
Any linkage with
Sorry.
graphics?
So you can generate dot files from a Racket graph implementation, and I have to thank JP Verkamp. I'm sorry if I'm pronouncing it wrong for that pull request, but it was a great feature to add.
May I please have some graph layout algorithms? Maybe that's, the dot is your answer.
Sure. I'll put it on the list.